Learned how to draw basic Lewis structures. And in this one, I'm going to add on to that a little bit because sometimes we break the rules. We break the octet rule. And that leads to an atom having more than 8 electrons around them. And actually, there is one case in which it will have less than 8. Most of the time, it's going above that. One of those exceptions would be PF5. So when you draw phosphorus, it has 5 valence electrons. So you have 2 that are already paired up, and then 3 that are single and ready to move. So if you were trying to draw it, you would connect 3 of the fluorines to the phosphorus, and then you'd say, there's no more room. But what actually can happen is, due to hybridization, the phosphorus can split up its unshared pair because, as it's in the third period, it has a d subshell. And any subshell contains orbitals, which are places where it's possible for an electron to exist. So what the phosphorus actually does, all you really have to do is draw that it separates, and then you have a single 2 available dots for bonding, and then you would end up with the formula of PF5. Why that happens is that in the third energy level, normally phosphorus has this for an electron configuration with 2 electrons paired up in the s subshell and 3 single p electrons available to bond. However, what can happen is that s, the 3p, and one of the d orbitals can actually hybridize, and when that occurs, they blend into equal energy orbitals, and you end up with the possibility of having each electron have its own orbital and then be able to form the additional bonds. So in order to accommodate the 4th and 5th phosphorus, it had to hybridize with one s orbital, 3 p orbitals, and a d orbital, giving it an sp3d hybridization, where you have one s orbital, 3 p orbitals, and one d orbital, blending together to form equal energy spaces for electrons. All right, and the other 4 d orbitals would be left unhybridized. Another type of funky thing I want to show you with Lewis structures is what can occur when you have coordinate covalent bonds. And this O3, or ozone molecule, has that. If you try to draw it, I mean, you could theoretically draw it as a triangular shape, but that actually doesn't happen. If you try to draw the Lewis structure, you could pair up 2 of the oxygen atoms and end up with a standard oxygen molecule. However, if you have an unbonded oxygen available there with 2 unshared electrons, what will happen is one of the unshared pairs on one of the oxygens will form coordinate covalent bond, contributing both of those electrons to the bond with that oxygen that only had 6 valence electrons. So now what would happen is you'd end up with an oxygen molecule, O3 molecule, where you have a double bond to an oxygen and a single bond to the other. And that can move back and forth. This is called resonance. Because it doesn't have to be this oxygen atom that formed here. It could have double bonded here and then had this one end up as a single coordinate covalent bond. The electrons are actually able to move back and forth within the molecule. So at first you have the single bond to this oxygen. One of those unshared pairs can dump itself in to form a double bond there, which is what we see here. And then, because that would create an unstable situation for the oxygen in the middle, one of the bonds in the double bond can pop itself back out as an unshared pair of electrons on the other oxygen atom, leaving it with a single bond there. So basically, resonance is when 2 identical bonds, one single, one double, the electrons move back and forth between the bonds, and that adds some element of stability to the molecule and lets it actually exist. Another example where that occurs is with the polyatomic ion carbonate. Carbonate has the formula CO3, and it has a -2 charge. So just to go over when you're writing these structures for polyatomic ions, whatever the charge is, that tells you how many additional electrons you have. Ammonium is the only exception where it would lose an electron, but usually they're negative, so this means that 2 extra electrons have been gained. And given the options of carbon or oxygen, the atom that would gain the electrons would be oxygen. It has a higher or more negative electron affinity, meaning it's more favorable for electrons to be added. So 2 of the oxygen atoms gain an electron. That means that each of those oxygens would only have 1 electron available to bond, and the other one would be double bonded. So you would end up with a Lewis structure like this. Now, it didn't have to be these 2 electrons that gain that electron. And in fact, because it makes no difference and it's not preferable to be on any of them, they're all equally favorable, the electrons can actually shift, just like we saw in the ozone molecule, and exhibit resonance. So all three of these structures would be acceptable. I left out the unshaped pairs on the other ones, but all of these are interchangeable, where double bonds and the single bond can move around within the molecule because each position is equally favorable. So in this video, we went over exceptions to the octet rule, coordinate covalent bonding, and what resonance is.